Okay, then now if you want to, yeah, then I have started the call sharing. This is from here that you start the call. Okay, and then now I'm trying to turn on the projector. This is the projector. And now we have the people who are showing up there.
Okay.
Okay.
So this okay.
And then is it okay? Then now I can sit with you. I can sit with you.
Okay.
I'm always doing all the.
Okay. Okay. So, but then the next question?
Yeah.
Do you have access to the? Did I hear?
Yeah, you can hear it. Okay. Can somebody on the line confirm that you can hear us, Daniel, or?
Yes, we can hear you.
But we cannot hear you. Okay, can you? Okay, we cannot hear you. Okay, then I see Daniel talk, but we cannot hear. Okay, then they have to see. Can you talk again? No, it's not working.
Can you hear me?
Perfect. Yeah, good. Thank you so much for being our guinea pig because okay.
No problem. And we are recording right now, just to let everybody know.
Okay, on the already recording. Okay, okay, this is great. Okay, okay, oh, just slide. Something this. Because this I don't have access to slides, otherwise I can. And Daniel.
Yes.
Okay, then where Julio is not there, he's stuck in traffic, and the other co-chair is going to help us to coach to chair the things, but she doesn't know where to find the slide. And this, I don't have access to the slide.
And I'm sorry, who did you say was stuck in traffic?
Julio.
Oh, Julio. Okay, yeah.
We need to have access to the slide.
Or maybe Daniel can.
Yeah. Who do you want me to send it to?
Can you send the link to yes? Can you send the link to? Yeah, you can send the link to me and to. Yeah. I don't know if he has your email. So, can you send the link to me and I can forward it to her? Yeah.
Okay, let me see if I can say
This
sure.
is Hannah@ucor.edu.
What would be
Good. Ready for your
I'm sorry, what's your last name one more time? I'm so sorry.
There's a lot
Thanks.
Can we go?
I think I'm done my scale because graduate school. I had to get
Everybody that we are recording already. Then anything you don't want to be on the web, and also we are trying to sort technical issues and don't be too loud because we cannot hear him. That's something on the line. But yeah, but just
don't yell. Don't say.
no, don't. Yeah, they're recording and they cannot get the recording. Sorry. Just
Okay.
know everything is recording already.
Nice talk yesterday.
Okay, so I'm gonna share this, share the folders. I'm so sorry. What's your last name one more time?
Hanay, Hanay.
Oh
Yeah.
yeah. Okay.
I think we'll have enough seats at the table.
Okay, so I'm sending it right over.
Okay, thank you.
So it's gonna be under so if you're looking for
Right? Yeah. Well, they all doesn't move.
Damon folder.
Follow it. Yeah, we had one for our. I sort of got a little involved in it.
Yes, okay.
Local
Then
politics.
I'm putting these, and then there are several.
City council or something?
We have a board of supervisors.
Okay, then I have the
We live in a
slide.
pretty
Okay.
small township, like 30,000 people.
Okay.
But there's been
disturbing.
Did you find access to the slides?
Yeah, then I have access to the slides.
local
Let me try to.
Oh, I was gonna
just
say,
look in
you're in
there.
Pennsylvania, right? Yeah, I guess. It's just. We're in half town. Yeah. But yes. I'd love to see you in person, not on. Yeah. And ask you or something like that.
Oh,
Yeah, you came up perfect time.
oh.
I was saying, like, I was joking with him, because he's out visiting George.
Okay, yeah, that's right.
For the next couple of weeks. Okay. Like, I get out here, and it's like 0 degrees, whatever, it's cold, and I'm looking, I'm like, oh, this weekend's gonna be nice, like, it's gonna be like 40s, 50s.
Yeah.
I'm going back central Pennsylvania, stratosphere, like 20 degrees again. Can't win.
Manage you here when it's cold.
Yeah.
Oh, it's cool. Did you see the temperature trace up here this morning?
No, I didn't.
High temperature was 14 degrees. at 5
Okay,
a.m.
I'm just.
Bunch of
wait,
waves.
but process-
Yeah, this morning.
Yeah.
Broke through the inversion.
Well, it's not breaking through down.
No.
And low.
Daniel,
It was warmer today at our house.
I am
Plus
one, I'm one of the co-chairs. I asked to join the school meeting.
I was on a call this morning at 7 a.m. Some guy sitting in Brazil, sun shining in his window. I'm like,
Yeah.
it's only about 35 degrees centigrade
Oh,
warmer.
but you can see the chat.
It was minus 17 at the time, centigrade,
They want you to-
0 Fahrenheit. Sun hadn't come up yet. Window open, and some office sleeves rolled up.
Oh, no.
St. Paulo.
Danielle,
Refer to that as
We
living
need-
dreams.
Yeah.
we need access to
I'm sorry. Okay.
HUI. We need to give access to waves.
Yeah. So it's not in Brazil
HUI.
in 6 months. Oh,
No,
it's not living
mine.
mine.
He's living sun. It's not called the
Do
dream.
you want me to share with HUI? I'm sorry.
Yeah.
Do we?
If you ask my undergrad.
It's HUI, W.
Little unclear.
2 weeks ago, I was on a call. It's like,
Okay. Sorry, I can't hear you. Can you chat? Can you put it on the chat?
Geneva.
Put on the chat.
I just.
It's like 50 degrees and raining.
Yeah. Exactly what I was gonna say. Yes.
Do you care?
It's not a great year to go skiing over here.
No, but it's a good year if you have to heat your house to buy energy. Geopolitically, this cold weather here saved everybody's ass. The price of gas is cheaper than it was a year ago.
Yeah.
They've been adding storage in
Yes.
January, which they never did. So it's been.
Yeah, tomorrow.
The irony is the cold, the warm weather goes all the way to Belarus. Moscow is freezing.
Well, I know, yeah, that Asia. Well, you know, China's cold.
I was gonna say, my justice, it's cold from Moscow to north to Pyongyang. No, Japan's getting it. It's pretty much that.
Okay, maybe this is the one. I was gonna say. Evidence of, higher.
Yeah.
How are you? Okay.
I saw it. Hopefully you're not going home before this.
I tried this. Yeah, I think we'll be out. I'm flying through.
Except over England,
Right now? My to-do person. Then this is showing. I don't know what's going on.
What otherwise shall I share? The browser.
Oh, I see. Share the
Yeah.
stuff first and then.
Yeah, exactly.
and just like them and
Um,
Denmark was just 0 C.
This is.
Colin?
Peter, how's it going?
I haven't seen you in person.
I've been telling everyone.
Didn't know you were
Yeah, this was the room. When I got the email, it was like, is this it? I was like sitting here. I was like, oh, this is good. And share that. Yeah. Oh, she got to make sure. Of course, at that time, it was 2 weeks. We're closing for 2 weeks.
This is 2 weeks.
Stop the spread and you'll get it going again. 3 years later.
Okay, but then I give to share first. Or?
Oh, yeah. Got an email from Chuck Bargan. Did it have any conservation errors there?
So where did,
What's
what did you find?
Well, we're getting all these.
I found out that the Chuck energy is triggering for the microphysics. Oh, no.
Mass errors, mass conservation errors.
And then so Chuck emailed us just now saying that he's finding mass errors. So,
I mean, we see that occasionally, but
yeah,
usually they're not significant. Sometimes.
we should talk about it. We just do these 9 time step runs and they're throwing like crazy. So one of our recent commit seems to mess up mass conservation.
Yeah, okay.
That's why Chuck just emailed us. And I didn't tell him, but he found something.
The problem is I see him.
Okay.
Yeah.
And then I think.
We also get on the club.
Yeah, I
We
know.
have a fix for
Lots
that.
of that. Problem is they often get scared. Club stuff and even the deep scheme.
Let's go back to the original one and leave this stuff, but then this one. Download everybody's slide.
And I think we can remove the people on the side where.
You could ask.
Okay, let me do
Yeah, I
that,
can look
but
it
I
up.
can do, yeah.
Let's leave this.
This one?
When's your flight
Let's
coming?
just leave this. Leave it like that.
It's
This is,
yeah.
this.
I was watching the end of the internet on board.
What?
Okay.
Except, the Greenland was not in northern Canada.
You lost the
Pretty
internet
spotty.
connection over Greenland.
Oh, you guys started at.
Yeah.
We knew
But I cannot.
we were over Canada.
Yeah, you can,
Okay, let's get started.
So
Hello,
It's
everybody.
an aerosol.
Welcome to the
It's not a-
Tuesday morning session of
It's not
the
That's a good point. The
WWG
check engineer
meeting.
would lump it together.
Julio is stuck in with the traffic, so Cecile and I will have to chair the at least part of the morning session for him. So first of all, 2 important reminders for everybody online and here in this room. We are being recorded, so please keep that in mind. And then a reminder to everybody attending this meeting in person. At 11, there will be a CGD seminar. So after this morning session, we will have to move to that room. So after these 2 reminders, let's get started with our morning session. Our first speaker will be Dave Randall, who will give us some update on earthworks.
Thank you. I decided to stand up here because I can see you better. So this is a very, and there are more names involved than you see on the slide. And also there's some related talks coming up by Bill Spamrock, who follows me this morning, and Brian Medeiros and Andrew Devon later in the week. So most of you know by now that Earthworks is a 5-year project funded by the computer science part of the SF, SCIENCE. And the goal is to, starting from CESM, develop a global storm resolving coupled model. So using a single nearly uniform grid for all of the components. So the coupler has less to do, but of course it's still there. So the components are CAM6 physics with the MPAS non-hydrostatic dynamical core developed at MCube. The MPAS ocean model, same grid, developed at Los Alamos, largely by Todd Ringler. And the MPAS sea ice model, which is based on the same sea ice physics as what CSM uses, but works on the impasse grid. And of course, the community land model, and we're using CMAX. So before we stress the importance of using the components of the CSM structure, including a specialist index. And we are working to preserve compatibility with the CESM code base. We don't want to break anything. And we also want to maintain all of the features of M-Cube, including regional refinement capability. And that's for both the atmosphere and the ocean. So our goal is, our target grade is 3.75 kilometer uniform and almost uniform for the bridge. Running on GPUs, and I'll have a brief comment on that later today. And the target systems are machines capable of running this by 2025, and that basically means DOT machines. But up to now, we've been using NSF machines, which I'll talk about. So initial objectives, port the ocean and atmosphere, the ocean and sea ice models into CESM. That was actually a pretty good job. That was done at CSU by Don Daslick and finished more than a year ago. So then assemble all the pieces into the intended configuration, which I've already outlined, and perform fully coupled simulations initially, which is 120 kilometers. And then along the way, test the impasse physics at the convection permitting grid spacing. And that's what Bill will be talking about. I'm not going to say anything about that today. And then according to GPUs, of course. And I'll say something about that later. So we've done both AMIB simulations and fully coupled simulations with 120, 60, and 30 kilometer grids. We've done aquaplanet simulations with all of the grids, very short at 3.75, but just a test. And we've done simulations with regional refinement. And today I'll show you some numbers from a test just in the last 10 days or so with a 3.75 aquaplanet on a NSF machine in Texas. So I talked about this briefly at both HQ and AMS, so most of you have probably heard this already, but we have to initialize the ocean model for a couple of months, of course. We have to initialize the sea ice. And in our first attempts, what we did was prescribe the sea ice in a very simple-minded way as shown here. So the yellow is the ice. You can see the white of the continental outlines. And so in the northern hemisphere, it was 2.5 meter thick ice. Everywhere the sea ice was present. This was a January 1st initial condition. And in the southern hemisphere, 2.5 meter thick sea ice from 60 south to the pole. In the northern hemisphere, 70 north to the pole. So this is pretty crude. It's too crude. So what we experienced is shown here. The ice starts too high. You can see my cursor. Starts too high. And it tends to increase with time. And of course, there's some attendant cooling that goes with that. We have something like a 1.5 watt per square meter top of atmosphere radiative imbalance. So that was no good. And Dr. Kogan, I don't see, but make sure I'll later. And Gokhan gave us some advice on using ocean model intercomparison project initialization protocol, which is quite a mouthful, as documented in a paper by Griffiths et al. Listed here. And it involves running the ocean and sea ice with data atmosphere for 62 years, 5 times. So that's 310 years of simulation. And during that, restoring the surface salinity. So there's more details here that I won't talk about. So we're currently doing this, and I expect to be able to report results in a month or two. We're doing this on the 120-kilometer grid course to start with. And then our intention is to initialize the ocean at high resolution by interpolating from a low resolution. So that's the plan, the revised plan. Andrew Fetter, who's sitting here in the blue shirt, is a graduate student at CSU, and he's in the early stages of a project to look at tropical cyclones in earthworks, eventually looking at something to do with climate intervention, but we're not there yet. So this is a single figure showing, you can see the red and green dots that represent tropical cyclones on a stormy day in 1994, the aim simulation of the 30-kilometer grid. Andrew essentially reformulated the tropical cyclone detection algorithm of Zhao and Hill that all listed down here at the bottom. Rewrote it using Python and has used that to produce some statistics. So on the 30-kilometer grid, Earthworks is producing 80 to 90 TCs a year, maybe slightly high, but in the ballpark. They have eyeballs and they move in a more or less realistic way in the right places. The wind strengths as measured by minimum surface pressure, the intensities as measured by minimum surface pressure are fairly strong on the 30-kilometer grid, like up to Cat 4 or so. But in terms of surface wind speed, they're only about Cat 2. So there's something not quite right there that probably involves boundary layer friction in some way. And I can't tell you any more details, but we're looking into this. It may have something to do with club, which we'll be hearing about later. One slide on GPU porting. So many of you probably know that the MPAS atmosphere was ported to GPUs by IBM and NCAR in a collaboration actually several years ago. And the MPAS Ocean was ported to GPUs by Los Alamos. And right now we're not worrying about the CIs, we're letting that go CPU. But the physics porting for Cam 6 physics is in progress. And the only thing that's really not there at all yet is Plug. And again, you'll hear more about Plug later today. So, as I mentioned a few minutes ago, we've recently run a very short, just a few time steps, aquaplanar simulation, QTC6, on the 3.75 kilometer uniform grid on 1,024 nodes of Frontera, shown in the picture here, which is at the Texas Advanced Computing Center. It's an intercept machine. And we have access to that, as well as some of the DOE machines. Frontera runs this particular configuration about almost 2 times faster than Cheyenne node per node. Frontera core is about 22% faster than a Cheyenne core, and we think the Dureco cores will be about 6% faster than Frontera. So there are some issues that we found at 3.75, and they're circled in red here. So the speed of the coupler is slower than we expected. Not doing much in an aquaplanar mode, of course. But the memory usage is not scaling as expected. But the big thing is here, initialization on the 3.75 kilometer grid is taking more than 3,000 seconds, almost an hour. So that's unacceptable. We've looked at the scaling on coarser grids. This is perhaps slower than you might expect on the 30-kilometer grid, but this we can live with. But 3,100 seconds is just not okay. And Rich Love's comment was that it appears that the initialization is scaling as if it was serial. So I don't know if that's the case, but this needs to be investigated. And so what happens with us, every time we go to higher resolution, we find a new problem. And this is something that's shown up at 3.75. So that's being worked on. I had a slide that I somehow moved, but relating to our goals, which I already mentioned, we're 3.75 kilometer uniform grid with 58 layers. So, stratosphere is not very highly resolved. Half a model year, half a simulated year for walk by 2025 on a DOE mission. That's the goal. And based on the results we're getting from TAC, we can estimate that this may be achievable on the GPUs that we expect to be available on those machines by 2045. So we'll see. But the goal does not appear to be out of sight. Let me skip ahead here because I have another slide and I know where it is. No, I don't. Somehow I deleted it. Well, sorry about that. It's a slide that I got from Bill Shamrock that shows memory scaling.
I think you already skipped it.
You skipped through it earlier.
How did I miss it?
Curvy line.
There we go. Okay. Lines, yes, this is the heavy line slide. So when we think about scaling, we often think in terms of wall clock performance, speed, but it's also possible to think about memory scaling. And that's what this slide deals with. So the idea is that as we, let's say for a given grid, we increase the number of nodes to try to make the thing go faster. That's strong scaling. Or we increase the resolution, make the grid bigger, but simultaneously add nodes in the same proportion. That would be weak scaling. And this slide kind of addresses both, again, in the context of memory, not speed. So this is a bit complicated, but down here you see results obtained with MPAS, and this is the M-cubed version of MPAS, the version that is not running inside CPSM. And the actual parameters of the simulations here are different, so the space between these lines and these is not meaningful. Okay, that's not the point of the slide. But the first comment to say is the change of memory per thread on the vertical axis with columns per thread, and notice the numbers increased to the left here, is as expected. You're seeing results on both the 30-kilometer grid in blue and the 60-kilometer grid in black, and looks pretty good. When we go to the version of the model that runs, and this is Aquaplanet again, running inside the CPSM infrastructure, we get these curves, and you can see there are various resolutions. These ones that don't have a line drawn through them are 15-kilometer grid. The green here are on the 30-kilometer grid, and so on. So there are sort of 2 points. The first one is that something strange is happening over here on the right side when we're going to a very large number of nodes for a given grid, essentially. The memory usage increases in a way that's not reasonable or expected. But we plan to be using on the order of, a few thousand columns per grid in actual applications of it. So we'd be over here somewhere. But over here, we see this separation. So the blue and the red curves are pretty much on top of each other here, but then the green curve is using more memory, and the pink dots are using even more, and we're only at 15 kilometers now. So we still have 2 more doublings to go. So this is another issue, and we don't know the cause of it at this point. But again, it does not happen in the M-cube version of MPAS. And I forgot to say that the initialization timing that I mentioned, the excessive initialization time, also does not happen in the M-cube version. So these issues appear to have something to do with the way CPSM is constructed, and we're looking into that. We'll find the problem. We'll fix the problem, and that will benefit everybody who's trying to run the model of Hyperloop. So we'll let you know, but that's all I can report right now. Okay, so back to the summary. We think we're on track to achieve our goal by the end of the first 5 years, but we have a lot more work to do. must be.
And your initialization time, is that kind of from a cold start, or have you tried restarting the model?
It's
Does it
from a
also
cold
take-
start.
Okay.
It's from a cold start. We, you have to run it once to have a restart.
Right,
So,
yeah.
And I didn't say this before, but roughly the first half of that initialization time, the IO rate is actually very small. It's like not reading anything. I don't know what's.
Okay. Thanks.
Quickly, is the land model on in those experiments?
That was Aquaplanet.
Okay.
So that's another issue that will bite us at some point.
Did you have any regarding the memory scaling issues? Do you have any idea if it's happening in physics dynamics coupled?
We talked about this in our most recent call. We just got the results 10 days ago. So we don't know yet, but that's one of the things we're looking into.
If I could say something to Peter's thing from our Frontera results, once you get to integrating, the memory usage is just flat and
That's right.
it looks very
Yeah,
good.
that's right.
It's something going on in initialization that's causing a high peak in memory.
So I can imagine that when the model was designed, people thought, well, initialization is cheap anyway, so we don't have to worry too much about how it's done. But in high resolution, it becomes a problem. That's what it looks like.
I'm trying to load Bill's presentation. So while Cecilia is working on that, let me introduce our next speaker, Bill Skamarok, who is going to talk about convective scale testing of MPAS with Chem6 physics. Slowly.
So what we are doing to test the physics at convector scale meshes, essentially 3 kilometer cell spacing, is that we're using the variable resolution capability of MPAS with a 60 to 3 kilometer mesh. And the 3 kilometer region is not very big, but it's big enough to hold convector systems, tropical cyclones, etc. And what we've done is we've run 2 test cases with the Chem6 physics that I'll show you some quick results from that give you a sense of what Chem6 physics is doing. And we made some modifications to it to try to get it to perform better, and that's what I'll show. A lot of people have contributed to this, both from the earthwork side, SEMA, people in MCube, so I don't have a list of 100 names, but there's a lot of them. And essentially, 2 tests. First one's a squall line. Here's the mesh you can see depicted on the right, and that inner circle is essentially cell spacing less than 4 kilometers. So we've got a fair amount of the central US. And what we're doing is just a forecast mode. So we're running a couple days, initialized from the GFS. This is with the 58 level configuration, which is kind of the workhorse one projected soon for CAM in that next release with a model top around 40 kilometers. So and I think it's reasonable to do convection with 58 levels, 32. So, okay. So this is the thing we look for. I realize this is kind of small on the screen. On your left is the observed reflectivity, and this is after a day of simulation time. The model spins up very quickly, so it's spun up in terms of convection. On the right here is a simulation with MPAS using morph physics, the standalone version. And what you see here is this is a classic squall line. You can see the bright red on the eastern side of that line. That's the leading edge that propagates from west to east. And behind it, the yellow reflectivity is the stratiform region. And you can see the same kind of signature in the MPAS simulation with morph physics. And this is kind of standard. Typically 3 kilometers, these models will kind of overdo the convection a little bit, and you won't see some aspects of the stratiform region, but you get most of it. So this is a reasonable simulation, and I would say this is more or less state of the art for models here, for non-hydrostatic models in this kind of event. And this is relatively strongly forced. There's a nice cold front coming through a baroclinic wave, but the convective system's out in the warm sector of that wave. So while the front kicks off convection, that system propagates out ahead, and it's kind of very standard squall line. So this next figure is what happens when you just run Chem6 physics, MPAS and CAM, Same exact setup, but just running CAM6, although we are running MG3, so that means we included a grapple hail category, if you want to think of it that way. And as you can see, well, for one, the stratiform region is way too large, it's too wide, and also the convection is not concentrated at the front of the line, it's at the center. And what's going on is it's staying tied to the cold front. We're not seeing a propagation of the system in here, so it just doesn't look very good. So, okay, that was first out of the box. And one thing we tried was one of the main differences between the microphysics, or the microphysics and macrophysics in CAM6 compared to most cloud model implementations, is the fact that the saturation adjustment is done inside of Club using the two moments, using the two PDFs. And so what we thought we would try is to collapse those PDFs to delta functions to try to mimic how it's done in the regular cloud models. And we did that. And what you get is the figure on the far right, which shows a much nicer squall line. But still, we're not seeing that convection, thin line of convection right on the left side, or on the right side of it at the eastern edge. And we're not seeing a good stratiform region. So we've gotten part of the way there, but not all the way. So that's one change we've gotten that's given us ways, at least in terms of the test. This is a depiction of a cross-section, a west to east cross-section of the potential temperature over the first 6 kilometers of the atmosphere. And if you look at the cold colors down low, the blues and the greens, that's the gust front. On the far left is the impasse with wharf physics. So what you see is a deep cold pool with a very sharp leading edge that extends up about 1 kilometer. And that's where the flow over that gust front is triggering new convection. And you can see in the middle one, the standard configuration with CAM6 physics, we're not seeing that deep cold pool at the leading edge of where that gust front is. When we make that change to the saturation adjustment, we can see that the cold pool looks a little better, but we're not seeing quite that depth and strength that we expect to see. So seeing that, we've actually gone into the MG3 microphysics and made a change to try to increase the evaporative cooling in the downdrafts effectively. And you can see we're getting a somewhat deeper cold pool, but you can see it's not quite as strong and as deep as we would expect from the other simulations and what we know from observed squall lines we expect to see. So essentially, we're moving forward with some tuning. We're getting better, but we're not quite where we'd like to be. We're certainly not state of the art yet, but at least there's a suggestion that perhaps increased tuning and changes might get us closer to where we want to be with the CAM6 physics, which is our goal. Okay, so tropical cyclones. We have simulations of Tropical Cyclone Maria. This was back in 2017. A lot of damage in Puerto Rico, for example, when this made landfall there. And this is the mesh we used, so you can see the 3 kilometer region down in the Caribbean there. It's a very strong storm during this period, Cat 4, Cat 5. It's been a very intense cyclone. And essentially, the simulation we're going to see from the models was done when it was always over the sea. So we're not dealing with any land issues here. Okay, so on your left is the standalone impasse with the wharf physics. This is top of the atmosphere OLR, and this is essentially a brightness temperature, observed brightness temperature from satellite. They're not the same color scales. What I want you to notice is that the scale of the tropical cyclone, the eye, the banded structure, you can see them in both, and they're about the right scale. And this is after 2 days of simulation. So, which is more than enough to spin up cyclones in the model. Absolutely. So this is a reasonable depiction, and this is kind of what we expect to see. So on the next slide is what we get with CAM6 physics impasse, same mesh, same setup, same initialization, just running CAM6 physics with MG3, the same depiction of the OLR, so we haven't changed the color scales or anything. And what you see is that we get a much larger system. We don't see the banded structure very well at all. And if you look at, for example, reflectivity and other measures, updrafts, the banded structure just does not look good compared to the observation. This is, I think, the experience with CAM6 physics on mesoscale grids, for example, maybe 30 kilometer cell spacing, that you get these big donuts, I've heard it referred to. They're easy to count, they're easy to find. but when you look at the structure, they're not what we want to see. So we made some changes, and this is the first change using the collapsed PDF and the saturation adjustment in Club. And right away, you can see, while it's still too big, but we're starting to see the banded structure. That's a good sign. That's a good sign. And we've made a few other changes, including we've changed the cooling in the downdraft, the evaporation. Plus, we've taken some of the changes that have come from the climate process team that's been looking at that Colin's been involved in, and a number of other people, including some folks at MQ. And now we're seeing much better banded structure here. So we're going in the right direction, but still it's too big. Although I'm not sure, given such a strong cyclone, that this is necessarily indicative when we make those changes of what we should expect on average. So we're going to be doing a lot more cases, but what we're trying to do is kind of get to the first order result that we can maybe sort of live with. So that's where we are. And this is the summary slide. Essentially, we've made some changes to the Camp 6 physics in terms of tuning or actually going in and changing code to collapse the PDFs. But essentially, I think we expected to make changes to the microphysics because they haven't been run at convective permitting scales in models very much. So we knew we'd have to do some tuning there. But I think the big question is, how do we address the PDFs in Club? And there's a group of us that are talking about that now, and we're going to look at some options in terms of how we do that. The last thing I want to mention is, especially on the variable resolution scheme, the deep convection scheme, ZM, it tends to scale its precipitation with time step. We'd like it to scale it with the mesh size. For example, in the 60-kilometer region of the mesh, when we're running the variable resolution with a 3-kilometer time step, we would like the 60-kilometer region of the mesh to have the convective parameterization, the deep convective parameterization, produce what it would using that 60-kilometer time step if you had a uniform mesh, and we don't have that yet. So we're going to be addressing that too. So that's what I have to say, and I'll be happy to entertain a few questions here.
Collapsing the PDFs in Club, is that acceptable in the lower resolution area of your domain?
So we didn't look there. In some sense, in the lower resolution, I'm assuming that Club is fairly well tuned for the half degree to degree meshes. So I would like to be able to leave it like that, to leave it to behave like that in those regions. But we didn't look to see what the precipitation looked like.
It's supposed to scale with the length. There is a length scale in there. It's actually supposed to scale with the length scale, so it should adjust, but it doesn't seem to be effective. So ideally, like he was talking about with the deep convection, there is a length scale term in there that should change the PDF as the mesh size changes.
I'm just curious if you did an actual direct comparison of a 30-kilometer tropical cyclone simulation with your 3-kilometer. Are they really similar?
So this reminds me of what I've seen from previous results. SE Core is doing the same thing. So this isn't a dye core issue. This is a physics issue, I would say. But we haven't done that direct one-to-one here yet.
Yeah, although to answer that question, I do think a lot of what we've seen at 3 kilometers is pretty consistent with what we've seen with like the NE 120 runs with the Camp 6 physics, as far as the structure.
Going 3 kilometers doesn't provide any new. It doesn't change the structure of the cyclones.
It does, but it does not. You know, if you think about like the Chris Davis philosophy of like, okay, if we turn up the resolution, that brings down the effective resolution and better resolves the core. It's pretty clear that there are physics biases still at play at 3 kilometers.
It doesn't fix the fundamental problem, I think.
Yeah. So I just had a quick question on your cross-section slide, the cold pool. I saw like in the lower left corner, there was also a very big difference if you looked away in kind of the trailing region.
So that depends on where the cold front is.
Okay.
So in the impasse with more physics front, the cold pool, the cold front had progressed just a little bit further east than what you see in the CAM runs.
Okay.
I don't think that's a problem necessarily with CAM physics.
Okay. So, because I mean, I know we've looked a lot, or you've looked a lot
right at, with the squall line, but I was curious to see in the ambient environment, either out in front of the squall line or behind the squall line, if there were also.
So I've looked at a lot of soundings there, because not only do you want to look at temperature, you want to look at the vapor and everything else that's going on there. And the soundings don't look that different out ahead of the line in particular, which is where you really want to see. Because that's one possibility that the club is messing up
Modulates
the environment, so you're not triggering, and that's not what's going on.
Okay, thanks.
Okay, thank you, Bill. Next, Adam Harrington will talk about coupling a variable resolution atmosphere to top two in CSM 2.2.
It's the wrong part.
Yes, sir.
Just hit full screen.
Okay, this way.
All right, if that's how we want to do this, let me try to at least force the gin joint.
Should we download it? Okay, from the participants' perspective.
Tuesday. I understand it's okay. Browsers are- So what I'm gonna do is just we'll try to read it or. This will work, I think. I don't understand maybe I can't open a PDF.
Test it out like.
Okay, I'm sorry about that, guys. I thought PDF would make it easier. So I'm gonna be talking about coupling a variable resolution atmosphere to up to 940s, unless usually done by 955 the latest. This is a joint CSM and CNA activity. On the CSM side, this is a longstanding cross-working group with the Land Ice Working Group. And then I also want to acknowledge Zeke Yin, who is a PhD student at CU, formerly under Jan Lenitz, until Jan moved to the private sector, and so his advisor now is Anish Samarian. So the outline is, I'm sorry guys, I just have to get a drink of water. Just give me 1 second.
Yeah.
Okay, so this is the Arctic grid. I write about it in this James paper. It's quarter degree resolution over the broader Arctic and 1 degree elsewhere. We run the CSM 2.2 code base. Go over sort of challenges such as tuning. Go over the PI control climate. I'll show a 1% CO2 experiment. And the focus is going to be on the Greenland ice sheet. And so SISM is on, and we'll be focusing on its response. The idea here is we want to compare it to the 1 degree workhorse and see what resolution does for us, if anything at all. So the challenges, there's 2 problems that we keep bumping into in using conventional physics packages on variable resolution grids, and inadequate scale awareness is obviously a big one, and largely unsolved. And this is just an example of how bad it can get. Where this is an aquaplanet where the IGCZ, half of the IGCZ is refined. And within the refined region, you get these much larger resolved updrafts that facilitate divergence aloft, and then downstream, outside of the refined region, you get convergence. So you have a grid-induced circulation that if you move the patch of where you find it, the circulation will move. So it's not physical. But we're refining the Arctic. There's not a lot of diabatic forcing and heating, so we really don't have to worry about that. The other issue is this very large sensitivity of climate to the physics time stuff. And I mean, I guess you could just run at the 1 degree time step and you wouldn't have to retune, but I don't think that's a very smart decision because, I mean, you have massive truncation errors that you're introducing if you use 2 coarse physics time step. And that's just illustrated with a simple moist bubble experiment. Multiple experiments, each dot is a moist bubble experiment, and the resolution is on the x-axis going from 1 degree to quarter degree. And these are the vertical velocities associated with those bubbles. And what you want to see is this 1 over dx type scaling, which goes with the pressure gradient. But if you hold the physics time step at 1 degree physics time step, so a half hour, as you go to quarter degree, these vertical velocities get more and more truncated. And what you want to be doing is maybe more resolved convection, but you're not able to do it. So I would like to do that. So we're gonna go ahead and use a small time step and retune the model. Basically, just to give you an idea, what I do is I just take a 1 degree model and I tune that with a small physics time step. That's good enough, it seems to be. It took me about 250 years of simulations, so about 1.5 to 2 million core hours to tune this thing, which I don't think is that unreasonable. So let me go into the actual simulation. So I branched off of this BG7 control, which you look at the global ocean temperatures of what I'm branching off of. This is just one leg of the control. And it's a slightly warmer, it's warming. There's a drift in the PI control, and there's also a drift in the PI control in the official CMIP6 deck CSM2 experiments shown in the black. And so our model runs a little hot. Here's me branching off with the Arctic configuration, and it does look like my climate's a little cooler, rest on's a little bit, maybe negative. And so we're going into a cooler climate. And this is what the SST biases look like in the control, where I'm branching from versus the Arctic. You can see the Arctic's a bit colder. but it also reduces regions where it was too hot. So the reason it's cooler is there's a 2 or 3 watts per meter squared reduction in solar radiation absorbed by the ocean. And that's not shown, but I'm showing here the cloud forcing changes due to my tuning. And as you can see, I thickened up the stratocumulus decks off of the coastal upwelling zones in the southern hemisphere in particular, and also in the Dicons region. And if you look at the SST change due to the tuning, you can see it cools the southern hemisphere. You obviously see a big cooling in the northern hemisphere over the polar cap. And that's because one of my tuning knobs was the albedo of snow over sea ice. And so you do have a colder Arctic and the sea ice thickens a bit. You see this warm anomaly over the AMOC Action Center. And if you look at the time series of AMOC, you can see that in my Arctic configuration, it's quite a bit more intense, at least for the small sample that I'm showing. And so if we take a closer look at the AMOC, it is more intense. This is what it looks like relative to the control I'm branching off of. So it's a good 25% more intense overturning stream function. And I didn't have to search very hard for a culprit. I realized it's not coming out too well in this plot or in this slide, but this is supposed to be the grid overlaid on the sensible and latent heat levels compared to the control. And well, I guess you can't see it, but there is a 25 watts per meter squared reduction increase in the latent and sensible heat fluxes over the AMOC overturning centers. And so it's likely, and you see it in the wind stress as well. And so it seems that the higher resolution atmosphere has storms with greater variability in the surface winds that are mapping onto the surface fluxes and pulling heat out of the ocean and facilitating greater deep water formation. That's my hypothesis. I think that's what's going on. I probably need to try to prove it wrong a little harder, but anyways, moving on out of the ocean and talking about Greenland. Greenland's a bit of a challenge because the precipitation rates are very sensitive to resolution in Greenland. And basically what happens is in this cartoon schematic of resolution sensitivity, is in your 1 to 2 degree models, you have a really overly smooth ice sheet. And as a result, that the storms that come in from the coast are not aggressively lifted by the orography, and they penetrate pretty far inland, and you dump a bunch of precip on the dome of Greenland. In contrast, in the 1/4 degree and 8th degree models, the Greenland ice sheet is sufficiently steep that it rings out the systems at the coastlines. Some of the rain falls into the ocean, some falls on Greenland. The net result is that your precip biases, which are shown here on the bottom, in 1 to 2 degree models are much larger than at 1/4 to 8th degree models shown here. And the Arctic grid is that 1/4 degree. Now, BG7 is what I'm branching from, and they didn't really want their Greenland ice sheet to be so ugly looking and huge. And so they employ really creative tricks for reducing the precip bias in the interest of time. I'm not going to go over exactly what they do, but it's actually pretty effective and interesting. So here's what the ice volume of the Greenland ice sheet looks like in the BG7 control, is in blue. And so if I lift the tricks and I just restart this run, again, I'm just running the workhorse 1 degree, we're not talking about the Arctic. If I lift the tricks, you get this purple line, and the ice sheet is now starting to grow and to become more faithful to the actual surface mass balance it's receiving. It's still spinning up. When I discovered this, I decided I wanted to redo the 1% CO2 experiment with a more accurate ice sheet for a better one-to-one comparison. So this one's almost spun up, but once it is, I'm going to redo the 1% for the workhorse configuration. The Arctic ice sheet is basically spun up here. I guess you have to take my word for it. And its ice volume is already less than the workhorse volume, which is what you expect based on the precip biases. And so this serves as our initial conditions for the 1% CO2. Let me just give you one slide on the sort of broad response of the 1% CO2 configuration in the Arctic grid. Here I'm comparing it to this Munchworth paper, which is the 1% CO2 experiment that has these hacks in the Greenland ice sheet. But we can still look at global metrics like this AMAC. You can see it's diving down immediately in both the Arctic and the control comparing it to. And I guess I should say this is what the 1%, this is what the forcing looks like. It's just 1% CO2 until it hits 4x CO2 and it's fully fixed. One first result is we looked at the transient climate response, and the solid line here is the Arctic, where the dotted line is the workhorse. And it systematically seems to be lower by a couple tenths of a Kelvin. And so it does look like there is a reduction in the climate sensitivity, at least in the short-term response, of which, you know, I could imagine 100 ensembles, and maybe this would be statistically significant, but we're going to continue to look into it. Lastly, I just want to go over the Greenland ice sheet response in the BG Arctic, because we did carry out the Arctic configuration in this 1% CO2. And well, the Greenland ice sheet is retreating rapidly. The ablation area is about 10% in the PI control, and it goes up to 50% at the end of 280 years of the simulation. This is the surface mass balance. The ablation zone in the PI control is just this little red zone, and then by year 280 or so, 50% of the ice sheet is in the ablation zone. So this thing's a goner. It's only a matter of time. And it's just not a sustainable ratio of ablation area to accumulation ratio. It also accelerates because the more the ablation zones expand, the more bare ice you expose, which is darker than snow. And so you see these changes in albedo that are accelerating the surface mass balance trend. You can also see, and this is what the ice sheet thickness looks. There's places where you're losing a kilometer and just of ice. And then lastly, we can look at outlet glacier detail, actually, because it's a 4-kilometer ice sheet mob. And so here's an example of Ryder Glacier in Northwest Greenland. The surface mass balance is at different successive years and more negative and negative. And so it's thinning and thinning the ice sheet, thinning this outlet glacier, less driving stress to drive glacier flow. And so the velocities of the flow velocities slow down. Same thing happening with Alpine Glacier in Southeast Greenland, but it's not retreating. Just an idea of the detail we get. And so that's basically it. You know, there's lots to talk about, but it took a lot of work to put this together. Is this something that people want to be able to reproduce my results? Is this a configuration that maybe we should think about supporting in CSM going forward? It's not very forward-looking because I'm using POP2 and we're moving to Mont 6. And so later this year, I may be doing a similar thing, coupling this dual polar grid to Mont 6. And so we could just wait until then to start supporting something like this. That's it.
So Adam, do you think your coupled tunings for the NE 120 VR would be useful? Because you did it at low resolution. Would that be useful even for doing like AIM simulations for VR runs? In other words, most of the planet but with the small NE 120 time set.
So you're asking whether it's worth tuning in AMAP configuration?
Well, no, I'm asking if your coupled tunings might work in AMAP or if it's not worth tuning AMAP.
I think they would map onto more realistic clouds in AMAP. AMAP has a buffer because you have the SSTs that are fixed. And so the clouds don't change quite as much as in the decomp set. But the general rule of thumb is you reduce the physics time step, your clouds go away. And so in AMAP, you do see a reduction in clouds, and so the tuning would be useful.
I'm curious about with that, you know, the ocean response and due to the increased winds, due to more downstream variability. So that must be a general problem that earthworks is gonna encounter, and anyone who's going to high resolution, that you or anyone know like what the strategy is to sort of deal with that as you move to high resolution to?
Well, we're realizing it as it comes down the pipeline, that this might be an issue. Is it an issue? Maybe, we like the overturning, the ocean circulation better with the 1/4 atmosphere forcing. I don't know, I'd have to ask Frank. Just in general, the variable resolution, experiments or projects that I'm involved with, we're just starting to find sensitivity of synoptic scale storms to resolution, going from 1 degree to 1/4 degree, 1/8 degree. This, the cold fronts become squall lines. You get deeper mixing in the atmosphere, and just the character of your synoptic systems actually change. And so you should expect, this changes in wind variability once you go out of the 1 degree world.
I was going to say a quick, I think, comment on that is the answer is yeah. Actually, what we generally find is that from a synoptic perspective, the cyclones don't really intensify that much more in the mid latitudes with higher resolution. Where we do see a lot of changes are in the structure of the storms, the gradients, and the wind variability, which I think is one thing you could be seeing. One question, well, I guess one potential thing is it'd be interesting to look at things like eddy kinetic energy or something that's higher up in the atmosphere to see whether that signal is kind of through the atmosphere or whether you're just getting it at the surface. And then my question is, it looks like you actually have the North Atlantic storm track riding right along that transition region. Have you looked, in general, I think these grids are relatively well posed, but do you have any thoughts?
It up there.
Do you have any thoughts on whether that's could be causing any issues?
When I remember looking at this, I remember emailing you many years ago when I put this grid together, looking at whether that was a problem. I was looking at Preckel right at that boundary, and until I see something, I think it's fine. But maybe we should be comparing storm trap locations in the 1 degree to the Arctic just to be sure.
Yeah, it's always an interesting question with these variable resolution meshes, especially when you get these, because you're looking at something that's very local, obviously, over Greenland, but then you have dynamics around the edge of that domain that are teleconnecting essentially to the rest of the circulation. So,
well, it's important to have a gradual mesh transition, and the Arctic grid does do that, and that's going to help with the scale and wire problem. You can really make the problems worse if your transitions too developed. Thanks, guys.
Thank you. So our next speaker is Patrick, who will talk about scale-dependent bias and the diurnal cycle precipitation.
This is work that's funded by CAMS 7 funding, and this is a revised and extended version of what I presented last month at WWG. So high resolution modeling at convection rod resolving scales has emerged as a useful tool to advance our understanding of the Earth's climate, but we're going to still have to rely on low resolution climate runs for the foreseeable future. So our goal here is to use the results of these high resolution simulations to improve CSM's usefulness as a hydrological model and to improve its usefulness for long-term planning under future climate scenarios. So analogous to the gray zone case study approach, we run coincident CSM simulations on a hierarchy of horizontal and vertical resolutions, and we compare the results with contemporaneous output from WRF. So from WRF, we have 3 one-year simulations that were run with a 4-kilometer resolution with a domain over South America. And using the refined region aligned with that WRF domain, a hierarchy of regional grids were created from 100 down to a 6-kilometer horizontal resolution, with each of those having a global base resolution of 100 kilometers. And for the horizontal grid, there are 2 vertical resolutions. There's the standard 32 level configuration and a 70 level layer configuration, where the lowest 38 levels are aligned with the WRF levels. So for consistency with the WRF model runs, the boundary conditions outside and along the perimeter are posed by strong nudging to ERA 5. So we focus our attention here on the mean diurnal cycle as it represents a dominant contribution to overall variability. The errors in the error cycle provide a measure of how well fundamental processes are being represented. And this mode exists at the intersection between the chaotic behavior of the weather regime and the larger scale variability. So with out of the output, it's a very large data set. And so we're going to start out small with just an examination of a single month of data for November of 2010. We're going to be looking at the variables of precipitation, 2-meter temperature, and 2-meter water vapor. The horizontal resolutions that we're going to show are going to be at the 6-kilometer, 25-kilometer, and 50-kilometer resolutions, because the other behavior of the other two resolutions can be inferred from these. For the vertical resolution, I'm just going to show the 32 level results. The 70 level results look similar, and basically the only difference is that the biases in 70 layer runs are larger. So this figure here is along the top panel. On top row is our CSM simulations at the 3 resolutions, and along the bottom is the upscaled WRF results that correspond to those resolutions. And so we know here that there's a warm temperature bias between WRF and CSM at all scales, and that there's a larger diurnal variation in the temperatures in CSM. We look at water vapor. We see that there's a significant persistent bias in water vapor associated with the Amazon River, and we see that there's the double impulse of water vapor that happens diurnally is substantially larger in CSM. So in general, the uptake and transport of water vapor in the Amazon basin is much too strong in CSM as compared to WRF. For precipitation, we first note the scale, the WRF precipitation compared to CSM at the 6-kilometer scale. For WRF, the precipitation is isolated into very small, very concentrated precipitation events, and as it's those are averaged over spatial scales, they form, you see them form into clusters of precipitation. Whereas for 6-kilometer CSM, you see strong cells of precipitation, but there's more widespread lower level of precipitation surrounding it. We also note specifically there's a dry halo along the Andes Ridge at all resolutions, and it's accompanied by a strong persistent precipitation over the Andes Ridge. So if we look at the mean profiles of water vapor for a cross section indicated by the lower yellow line in the figure there, we see that their CSM profiles compared to WRF all indicate there's anomalous water vapor over the range, and those with contours that roughly aligned with the model levels. As we move the topography, it provides a better view of how WRF maintains a sharp gradient of water vapor along the model levels, whereas for CSM, the gradient is smoothed out substantially. And at 6 kilometers, the CSM results better maintain the sharp gradient, but there's still leakage that does occur. That's not shown here. So our fundamental goal is to improve the CAM simulations running at climate resolutions for extended period of times. And so this specifically requires that we need to be able to demonstrate an improvement in the fidelity of results across scales. And we also need to demonstrate a quantitative improvement in predictive skill. So to utilize the hierarchical model simulations that we have to systematically improve the climate simulations, we envision a workflow where started the traditional way where you do the intercomparisons of data and you develop some new parameterization or some model modification. Then through a series of short-term restart simulations, you install and verify and tune that for testing. And once you're satisfied that, you're going to run those modifications through a full set of hierarchical grids to get a quantitative assessment of how the resolutions are what determine the impact of the modifications have on scale-dependent bias. And then to finish it up, I want to get a quantitative assessment of how the modifications improve predictive skill. And then once a modification demonstrates an improvement in scale-dependent bias and predictive scale, then we want to generate a new improved state-of-the-art result that becomes our new reference, and we want to iterate through this this development cycle. So for the download results, we saw that there was an excess of water uptake from the surface in the Amazon River. We saw warm bias in 2-meter temperatures. There is also a bias in the strength of the trade winds of the Amazon that I showed in previous talks. And there's also the large bias associated with precipitation associated with topography. And while these results, the CSM results better resemble the WRF results as the horizontal resolution increases, these are fundamental differences that are generally uniform across all scales. So here we're going to focus on just from here on out, just the orographic precipitation. And from an analysis of the results, I saw a discrepancy in the governing equations ability to represent tangential motions along the surface boundary. From that, it could develop a corrective term and presumably come up with a justification for a corrective parameterization. But there were also diagnostic tests that showed and suggested that the problem might originate in the spectral element dichord itself. And so what we really want to avoid is a situation where we develop a parameterization at mass and underlying problem with the dichord equations. So a review of the governing equations to look for possible discrepancies started with replacing the hydrostatic balance with a hydrodynamic balance constraint, for which we placed the assumption that all vertical accelerations vanish with a requirement that only the accelerations normal to the model surfaces vanish. And this results in equations that are very similar to the hydrostatic equations, but there's an additional hydrostatic defect term, which depends on momentum and contains higher order terms that become relevant at higher resolutions. And there are also two distinct constraints for a wet and a dry atmosphere. And so when implementing this balance in the wet and dry equations in the model, it revealed that there was an inconsistency in the governing equations, which implicitly assumed that the model levels, the moist levels and the dry surface levels all coincide with each other. So if we take the moist surfaces as the model surface heights, then the resulting hydrostatic deviation correction terms that result in the modification carry the effect of moisture in the dry equations. In addition to that, there were some moisture advection terms added to the thermodynamic equation. The gradient of pressure had substantial numerical errors, so we had to be done about that. And for damping, hyperviscosity is perhaps not appropriate for low-order truncated polynomial functions. Rather than acting to remove the variations at small grid scales, the upper actually results in bilinear adjustments to the element mean values. So basically, the current implementation of the hyperviscosity damping violates every single one of the conservation principles. So the possible solution is to replace the current damping with an alternate spectral damping, which allows for selective removal of the grid scale variability, and more importantly, to ensure that the form of the applied damping does not violate the conservation principles that the governing equations are based on. And one last mathematical inconsistency, which is related to the wet-dry problem, is that if the relations in the two blue boxes are true, then the relation in the red box is also true, which means that anywhere that the hybrid vertical coordinate is used on dry surface pressure is a source of error in the model. So to implement these modifications, we did a series of 2-month restart simulations from the beginning of October for the 50-kilometer, 32-level grid. And that allows for a 1-month spin up of the atmosphere to acclimate itself to each modification. And there are a number of degrees of freedom in all these changes, so it's required a lot of low resolution test simulations.
And I'll show two recent results. The first one is for this test, modifications 1 through 3 have been implemented and installed, but the hyperviscosity damping has only been replaced in the energy and mass conservation equations. The association between the anomalous topography, topographic precipitation, and hyperviscosity can be observed for this configuration by varying the strength of the damping. So if the damping is too weak, you start getting grid-point precipitation, shown on. And as you increase the intensity of the damping, then the problem of topographic precipitation emerges that much stronger. So for this test, I kind of found the minimal value that balances these two extremes. And I'll show the results for that. And for the last result is the same as this configuration, but the tracer hyperviscosity damping in place with the alternate spectral damping. So here the case with the dipole modifications are in the middle column, and on the left are the corresponding WRF upscale WRF simulation results, and on the right are the original reference simulations. So we see here that for temperature, the bias in the Amazon basin and along the Andes is reduced. And for water vapor, we see the reduced amplitude and the water vapor surges, and particularly away from the river. For precipitation, we see that the dry halo is mostly eliminated, and the precipitation here is more localized into stronger migrating cells. And there's a corresponding decrease in the precipitation over the Andes Ridge. For the water vapor profiles, show us that the revised model is better able to maintain the sharp gradient in water vapor along water levels. And for the last result, if you look at the monthly mean precipitation with the alternate spectral damping for tracer equation, we see in the middle here that the dry halo inherent precipitation of the ridge has been eliminated. And if we look at the comparison between the WRF results and these results, precipitation better resembles the upscale WRF result. So this is a work that's still in progress, so it's still a bit to do. So to complete the workflow for these modifications, I need to finish the implementation of and testing of the tracer damping, then move on to replacing the damping of the momentum equation. And then I'll be to the point where then I'll want to run through the sequence of grid hierarchies to evaluate its impact on the scale dependent bias. And based on these results, it seems like we should get some good measurable improvement. And then we want to run that through the predictive, the S2S framework to get a measurement of how the predictive scale has been affected by the changes. And we'll complete that and repeat the process next time, maybe focusing on the 2-liter water vapor anomalies. So in closing, I just leave with a question for WWG, and that is, should we establish a standard set of regional hierarchical grids resolutions to evaluate model revisions? This would involve developing a standard analysis tools with fixed metrics that give quantitative measures of bias as a function of resolution. And with the ultimate goal is to provide quantitative measures that can be used to maintain benchmark scores for scale of our scale and to quantify the current state-of-the-art results for model under comparisons. And that, thank you.
Yeah, just a quick question with your updated simulations. Have you also looked at anything like the kinetic energy spectrum to see how anything is getting modulated at those very small scales with your updates?
Yeah, not that far along yet. Just trying to get it in there. Yeah, so I haven't gotten to the where. Let's see how it does with all these different metrics. So, yeah, not that far along.
Okay. Yeah, cool. Thanks.
Thank you, Patrick. So our next speaker is Xian'an Jiang, who will continue with the topic of diurnal cycle in high resolution simulations. But Xian'an, could we ask whether you are able to share your screen and control your slides?
Yeah, can you hear me?
Yes, yeah, we can hear you.
Yeah, I will try to share my screen.
Please give it a try.
Can you see my screen right now?
Oh, yes, I can see your screen. It's not in full screen.
Okay, I
Not
will.
in slideshow mode yet.
Good enough right now. Should be.
Well, good enough, I would say. Then take it away.
Yeah. Okay. Thanks. So everyone, my name is Xuan Jiang from UCLA JPL Joint Institute. So this work is a close collaboration between our UCLA JPL team, including myself, Long, Joel, and the NCAT team, the Patrick, Adam, Julio, and Rich. So this study mainly will analyze the regional refined the CAM6 simulations that Patrick just introduced. So we mainly focus on the down cycle of the Eastern Amazon region. And this study is supported by the NSF CPT project. So as we know, the Amazon River Basin plays a crucial role for the global hydrological and carbon cycles. Therefore, the accurate representation of key climate processes of this region will be crucial for regional and even global climate projections. So in this study, we mainly concern model representation of precipitation over this region. Actually, based on this slide, you can see that our current climate models shows serious bias in simulating the seasonal mean precipitation over the Amazon region, particularly during the spring season.
So we are still seeing your title slide.
Yeah, we're not seeing presenter mode. We're seeing
Oh, really? It's a
normal
little
mode.
delayed, seems.
You may have to just present in normal mode.
So you are still seeing the first slide, cover slide.
See your title slide is also if you were editing your slide.
Yeah, I don't know.
So it's
Yeah.
more important. We are seeing the third slide now.
So it's better, right? I will try to make it larger. Yeah.
Yeah. Okay.
Yeah. So yeah. So this slide shows our current model that shows the serious bias in simulating the seasonal mean precipitation over the Amazon region. So here we've mainly focused on the volume spring season from March to May, MAM. So that this panel shows the MAM seasonal mean, the mean precipitation based on the GPM observation. So in this study, we mainly focus on the eastern part of the Amazon region, so near the coastal region. So marked by this green box. So actually we can see this observed rainfall maximum during the MAM over the eastern Amazon region is largely significantly underestimated in climate model simulations, including the CAM6. So shown here, this is the MAM seasonal mean precipitation simulated by the 1 degree CAM6. So which shows only a pattern correlation less than 0.7. And we can also see the dry bias over this East Amazon region with the southward shift of rain belt. And the more serious model bias is found in this club MF version of CAM6, so which is under development. Actually, the S2 just introduced in tomorrow's talk by Joel that this model actually can generally capture the climatology of global precipitation and the cloud. But in this case, we can see the East Amazon, the MAM rainfall is almost completely missed in this model. And this dry bias in East Amazon region is also very typical the problem in sim physics model. You can see that this is ensemble mean based on more than 20 models and also the individual model. Then in order to understand the model bias in simulating the seasonal mean precipitation over eastern Amazon, this slide shows the climatological, the diurnal evolution of precipitation. This is based on the GPM observation and the 2 Chem6 model simulations. So we can see that based in the observations, the seasonal mean precipitation over this green box region over eastern Amazon is largely characterized by the significant the diurnal evolution of rain belt, which firstly appears over the coastal region in the early afternoon, then propagate westward into the inland throughout the nighttime. However, you can see in the Chem6 models in this case is 1 degree simulation. You can see this diurnal evolution of rain belt is largely missed in the 1 degree, poorly simulated in the 1 degree, the Chem6 simulation, and almost completely gone, missed in this club MF version of Chem6. So these results suggest that the model bias in simulating the seasonal mean, MAM mean, the precipitation of this East Amazon region could be closely associated with the model bias in diurnal cycle. So this is the main motivation of this study. So in the following, we mainly focus on 2 points. So the first question we want to address is what's the key processes regulating diurnal cycle rainfall over the East Amazon region? And then we want to explore the can representation of this diurnal cycle over the Eastern Amazon be improved in high resolution chem simulations as Patrick introduced the regional defined these simulations. So for the first question, actually, we mainly focus on based on the observation. So the specific question we want to introduce address here is what controls the westward propagation of diurnal rainfall events over the East Amazon region? Which you can see very clearly by this the Haumüller diagram along the equator. So here is this is the time repeated for during 2 days. This longitude, this coastal region. So for this analysis, we mainly borrow this precipitation buoyancy framework, which is recently proposed by the Fayaz Ahmed and David Neeling et al. Paper. So the main idea is that based on their close relationship, then the lower troposphere buoyancy can be used as a proxy for the convection. So this equation is for the lower troposphere, the simplified version of the lower troposphere buoyancy, which contains 2 terms. One is the corresponding to undiluted Cape. Another is the moisture deficit. Then the lower panel shows the Haumüller diagram for corresponding to these 2 terms. So we can see that although Cape may explain some of the convection onset near the coastal region the diurnal convection, but we can see the systematic westward propagation of the precipitation is mainly dominated by this westward migration of lower troposphere, the moisture deficit. So since this moisture deficit involved with the difference, the theta E and the saturated theta E, then the further analysis shows that this moisture deficit is largely dominated by the westward propagation of the lower troposphere moisture. And meanwhile, this effect can be amplified by a cooling effect during nighttime when the convection propagates into the inland due to reduce the saturated theta E. So the next question is we want to answer what lead to this westward propagation of the lower troposphere moisture. Then we analyze this is moisture budget at the 11 p.m. At this time, the convection is located over this longitude. So this is vertical versus longitude along the equator. See, this is directly output from the EC model. So we can see the corresponding to the strong westward propagation of the moisture, we can see the the moistening to the west and the draining to the east of the convection in the lower and the middle troposphere. Then if we average the moisture tendency vertically in the lower troposphere, we can see this is the total moisture tendency. It's largely due to two canceling terms. One is the moisture sink due to convection, and the moisture source by the dynamics. Then if we decompose this dynamics into the vertical advection and the horizontal advection, we found the vertical advection almost completely canceled by the moisture the reduction by convection. And this total moisture tendency, namely the moistening to the west and the draining to the east, is mainly contributed by the horizontal advection of moisture. So as we know that during the MAM season, the eastern Amazon region is characterized by easterly wind, which is the so-called the Amazon low-level jet. So this results suggest that the westward propagation low-level moisture is largely contributed by the horizontal moisture advection by this easterly low-level jet. So this finding will be used to examine the model results. So next, I will move to the model simulation of in the regionally refined the CAM6 simulations. So we analyzed the five simulations with horizontal resolution ranging from 1 degree to about the 6 or 7 degree Patrick just introduced. So this slide shows also the climatological, the down cycle, down evolution of rainfall, based on the 3-year simulation during the MAM season. So we can see that again the observed this down evolution of particularly establishment of this the rain belt over the coastal region in the early afternoon is largely missed in the low resolution simulations. And started to emerge, we can see started to emerge in the higher resolution. For example, this is the quarter degree. And we can see that this propagation of rain belt can be reasonably well resolved, particularly in the highest resolution, the 6 kilometer. So, which is more clear showed by this Haumüller diagram. Again, we can see the westward propagation of the diurnal convection. In the observations is largely missed completely missed in the low resolution simulations, and started to pick up in the higher resolution, particularly in the 6 kilometer simulation. We can see the reasonably well resolved this westward propagating the convection, this with onset near the coastal region, this coastal line, the dashed line. Then we want to understand how the increased resolution can improve this simulation of diurnal westward propagation. So this shows this is total precipitation in the 5 simulations. Then we decompose the total into the convective and the large scale convection. We can see the improvement of this westward propagation is mainly through enhanced this large scale precipitation, while convective precipitation tends to be decreased with increased horizontal resolution. So this results is largely consistent with previous studies regarding this high resolution modeling. Then the question is that based on our previous study, the observational results, the westward propagation of convection can be largely contributed by the westward propagation of low-level moisture. So this motivated us to further check the diurnal evolution of the low-level moisture in these 5 simulations. Actually, it's a little surprisingly, we can see that regardless their horizontal resolution, all these 5 simulations can capture this westward propagation of low-level moisture reasonably well. Particularly, for example, this half-degree simulation, the this shows the smooth, the westward propagation of the low-level moisture, which is comparable to the highest simulation, the resolution, the 6 kilometer simulation. So these results suggest that the difference in the convective behavior in these different simulations could be due to their different convective response to lower troposphere moisture forcing or buoyancy forcing. So this is supported by this last slide I have, which shows the relationship between the precipitation versus the lower troposphere buoyancy. So this is the total precipitation and buoyancy. The cold color means that represents the lower resolution, and the warm, the higher resolution. So we can see that with the increase of the horizontal resolution corresponding to the same value of the lower troposphere buoyancy, we can see the precipitation significantly increased in high resolution simulations. So this enhanced the sensitivity of the precipitation in responding to the lower troposphere buoyancy is mainly through the larger scale precipitation, as we previously mentioned. So this results suggest the need of the scale awareness when parameterization accumulates. So I think this is the main results I have. So very brief summary, we found that the diurnal cycle rainfall over the eastern Amazon plays a crucial role for the seasonal mean. And we found that the low-level moisture play is critical for the westward propagation of the diurnal rainfall. And the improvement of the diurnal westward propagation rainfall events over the eastern Amazon is mainly through the improvement of the larger scale precipitation due to the enhanced sensitivity in responding to the lower troposphere buoyancy. So this is all I have.
Thank you, Sienna. Any questions from the audience here? I don't see a question online. So then, in the interest of time, let's move on to the session.
Can you stop sharing that we can share?
Yeah, I will stop sharing. Yeah.
We will be talking about using variable resolution to examine orographic effects around the Andes. We will get the slides shared.
Sure.
Oh, you should. Sure. Is that easy? Just for the almost. Oh, yeah.
Okay.
Okay. So I know we're running very late. I'll try to be really quick. I'm going to continue on the theme of South America. I'm using the variable grid that Patrick developed and talked about to try to learn something about orographic flow around the Andes. Usual background. So anyway, this is what I'll be talking about. I'm going to show nudging tendencies and then a machine learning model to try to learn about the tendencies and then some questions, etc. So orographic drag may not need any introduction, but just this is a nice kind of cartoon that shows all the different sorts of things that happen around topography.
you know, mountains are barriers, so the air has to figure out what to do, go around, go over, etc., or just get blocked. Anyway, so these are the things that high resolution might do better than low resolution. And the idea here is to use Patrick's grid here at the highest resolution that Patrick ran, 7 kilometers or 6 kilometers, somewhere in there. I'm using the 32 level configuration. I should mention these are very preliminary results. I'm not expecting this to turn into a parameterization time soon. But anyway, so what I'm going to look at are nudging tendencies when we coarsen results from the 7 kilometer, 32 level South America grid with no convection. Not that it really matters for what I'm doing. So this is what I'm using, and you all might express skepticism about hydrostatic, non-hydrostatic. I don't think for orographic flows, especially at low levels, that particular problem is too important. But as I said, this is all very preliminary. So nudge, what I'm looking at here is the so-called nudge to find approach, which was, I don't know who proposed it first. I'm aware of the fact that it's being used by Chris Bretherton's machine learning modeling group. So basically, nudging is linear relaxation to a desired solution with some time scale. In nudge to find, you take a fine model, a high resolution model, and coarsen it in some way, and then you nudge the coarse model to that to the coarsened fine model. So as I said, Chris Bretton's group is looking at machine learning combined with nudge to find. And one issue is that nudge to find around topography can be tricky. So the first issue we have to contend with is how to coarsen things when there are big mountains in the middle of your domain. So this tries to illustrate the problem. So over here is the 7 kilometer topography from the Sam Wharf grid. Here it's been conservatively remapped to the NE30 or 100 kilometer grid. And here is what we actually use in the NE30 model, which, since all dipores use some additional smoothing of topography, just kind of conservatively coarse graining topography to your model grid is not really actually used as the bottom boundary, and that's part of the problem. This bottom here is the difference between the top row and this actual topography used in CAM. So the issue is that everywhere you see red, it means there are big peaks sticking out of your bottom topography, and that's what the nudging has to contend with. So I'm advocating, or at least what I've tried in this study is the simplest possible solution. Well, there actually is a simpler there. What do you do in these situations? So what I'm trying to illustrate here is the problem. That is, your smooth topography actually is below the just coarse grained topography, and you have to figure out what to do in these points where the coarse grained topography is actually above your smooth topography. So in the, I think the standard nudging application is you actually don't do anything. You just use whatever the coarse grading gives you on this smooth grid. I've tried a different option, which is just to zero out the subterranean, sort of the subterranean winds on the coarser grid. So I'm calling those the null option and the block option. So these just a summary of the steps to go from the high resolution variable mesh to global nudging on 100 kilometer NE30 SE grid. So let me just probably skip this. It's just a list of the runs that I've tried. there's the basic run here is to turn off the gravity wave scheme totally in the NE30 and nudge then to the regridded fine. So I'm turning off the gravity wave scheme in the model and nudging to the fine model. And that's supposed to tell us about orographic flow. All right, so these are the mean nudging tendencies when you turn off the orographic drag in NE30. And the three rows, top row, are the nudging tendencies when you zero the winds in these subterranean coursing points. The null is the standard, I think, approach in nudging studies, and this is the difference. And you know, it's not surprising. The block option shows that there are stronger tendencies in nudging when you zero out the wind in the topographic sort of that projects above your model grid. And you know, this projection of topography above your lowest model surface is an issue even when you're dealing with reanalysis, because reanalysis topography is not the same as the topography in the model. So anyway, there is a difference depending on how you prepare data for nudging in this sort of nudge define approach. So you do have to, you know, I'm not claiming at this point that one approach is better or not, but you do have to realize, you have to accept that there is an impact on how you nudge, on how you prepare the nudging data over a complicated terrain. All right, so talking with Colin a few months back, he encouraged me to try Scikit, which is a fairly simple to use machine learning package. So this just shows, I'm trying to illustrate what I'm doing. So the first thing is you have to prepare some input data for the machine learning algorithm. And this red box here shows the structure of the input data that I'm putting in. So I'm only looking at the 11 lowest model levels, UV, the winds. I also, because it is a part of all gravity wave schemes, I'm putting in the stratification. I want to put in moisture eventually, but I haven't done it yet. And then also optionally, there are ridge parameters in each of the grid boxes. So this input data is a list of columns basically, with 11 values of the meteorological profiles plus ridge parameters. Then the target are these nudging tendencies. Again, I'm using the lowest 11 values from the run in which there's no orographic scheme in the course model. And then this is all thrown into a random forest regression. So this is the basic result that I want to show. On this side over here, on your left, is a scatter diagram of the predicted tendencies from the machine learning, either nudging tendencies or both U and V at all levels, versus the test tendencies. So this is what the model actually sort of, these are the actual nudging tendencies from the model. On this side is training with meteorological profiles plus ridge information. And on this side is just using the meteorological profiles. So, you know, there's clearly just meteorological profiles does a lot, but the ridge information, the subgrid, let's just call it subgrid topography information, does introduce useful, it appears to introduce things that the machine learning can use to make a better prediction. So another view of that is this, where this just shows sort of, doesn't come out very well. There's a very faint cyan line there. This shows the correlation and slope of, you know, the scatter plots that you would have at individual levels. So going from the surface to an altitude of about 3,000 meters. So these are just what, you know, these are just this plot, but at each level. And I'm looking for the slope of the scatter plot, which tells you, you know, how much bias or sort of, you know, does the machine learning exaggerate or not the prediction, and the correlation, you know, does it fit a straight line? So the correlations are high pretty much everywhere. You know, there's this, I think, meaningful structure that, you know, the machine learning model is doing a better job predicting things at lower altitudes. But, you know, there's still, at least in the correlation, some skill as you go higher. The slope is also best predicted, you know, so the one-to-one relationship never actually, you want one everywhere. You never get close to one really for the slope, but you do get closer at low levels. And also there is, you know, again, obviously from the last plot, there's been some information imparted by the ridge information. So I'm going to skip this. I think there is, I'll just say briefly, there is an issue. What do you really, you know, are the learning tendencies really model error? And I'm not so sure that that's true, but for now, we'll pretend that, you know, well, we'll just leave it at that for now. So anyway, I'll just stop here. This is a summary. I think, you know, details on how you port frame matter and much to find. I think I didn't talk about it, but I think we need to worry about what model error really is and how to figure it out. I do think information for subgrid topography, if you wanted to replace orographic drag with machine learning, you would want to include something about subgrid topography. And then, you know, in the future, there are all the diport issues that Patrick mentioned. You know, you might want to try a different diport. We should investigate the structure of the machine learning model. You know, what exactly is leading to this drop in skill with vertical, with the vertical? Are there other machine learning models that would do better? In particular, you know, I think it might be interesting to look at models that spread the training around a little bit in neighboring grid cells, because I think, you know, this all assumes we can do things in columns, which may not be true. And finally, I think, you know, we need to understand exactly the relationship between nudging and model error.
Immediate questions?
Do you think 6-hour cadence is enough for training your machine learning experiment?
Well,
or just try out, just try out?
Since, you know, my approach here doesn't involve anything. Like, these columns are all independent, you know. I actually shuffle them. So there's really no time evolution here. You might want to, you know, convolve.
You have meteorological profiles in this sense. That's diurnal variation.
What I'm saying though is that this machine learning just takes a profile. It takes a bunch of profiles of input and a bunch of profiles of output and does a fit. It doesn't know about whether the profiles have any relationship with each other. They're just independent profiles.
No, I'm talking about sensitivity to a training data set, because you have to train machine learning. So if you use for...
Okay, I guess what I'm saying is, I'm not sure 6 hourly would make any difference more than having, 100 years of 6 hourly data versus 6 months
No,
of
I'm
hourly
talking
data.
about just on the diurnal cycles,
Yeah.
not about years.
Yeah, you may, yeah, the
Because if you
assumption
have-
here is they're independent and it may not be independent. I would say it might not be independent in 1 hour, but it's an interesting question.
According to Patrick, what
Yeah.
he showed diurnal variations, so
Yeah.
I believe might be influence. I'm not claiming, I'm just curious.
Right. So we're at the break and at 11 we have a seminar.
So we're going to give ourselves some minutes to take a bio break.
Yeah.
And go to the seminar. For online participants, if you are interested in the.
Yes.
Pushed everybody back on the schedule.
Oh, yeah. And then-
How many grad students does it take to open a PDF? Any questions?
It is, it works. Yeah.
Must be forget faces. So in this complicated system.
Yes. Yeah. Well, I mean, it's like, you know, the URL.